Okay, so we know that the answer to this question is 3h by 4. We have discussed, if I'm correct, how many cases were there? I think it's 5 cases. Center of mass of a uniform cone, one solid uniform cone, two center of mass of a hollow uniform cone, three center of mass of a hollow uniform cone cut into two halves. Fourth was center of mass of a solid uniform cone cut into two halves. Okay, so yeah, so we discussed 4 cases, right? Yeah. So we have written these 4 cases, the formulas for these 4 cases. I do understand that. Now let's spend some more time to understand how do we arrive at these formulas. Okay, so this solution will be just a very short one. We just quickly have a glance through the derivation. So I have, in the coming solutions will be in detail discussing about the center of mass of a cone, both the orientation, one in which this is kept upright and two just kept inverted. Why? Because as we discussed in the case of hemisphere, I think I didn't solve the hemisphere when it was inverted. So it is always important to understand the position of the derivation of center of mass when we talk about three-dimensional regular figures, when they are aligned differently with respect to the 3D space. Okay, so let's spend some time to understand upright cone and inverted cone, and this question we'll do inverted cone in short, and then we'll discuss in detail. So when we say that the cone is inverted with respect to the xyz plane, okay, we assume that the height of the cone is varying along the z-axis, and the height is causing a change in the diameter, and therefore the radius is a function of height, which being the z-axis is a function of z. So radius of this cone is a function of z, and it varies from 0 to maximum radius r here. Okay, so yes, the side profile of this, which means the slant height here, it varies from 0 to 0, 0, at this origin to h comma r, which is this point over here. Okay, now if I consider this cylinder, this cone, and if I consider only the triangular part of this, I can draw this one more time over here and label this triangles as triangle OAB, which represents the one with the capital R, and triangle OCD, which represents a triangle with the base R of Z. So triangle OAB, capital R, H, OCD, R of Z and Z. Now we know that these two triangles are similar, and since these triangles are similar, the corresponding sides of similar triangles have to be what? To be proportional. And since they are proportional, we can write the corresponding heights should be equal to the corresponding radius, right? So OA by OC should be equal to AB by CD. OA is H, OC is Z, AB is R, and CD is R of Z, and therefore we can write that R of Z, is equal to R into Z by H, right? So we can write that. We can write that R of Z is capital R into Z by H. Now what is Z bar? Z bar is integral Z dm by integral dm. Now integral Z dm by integral dm can be written as integral Z dv by dv, integral dv. Why? Because dm is rho into dv. Plug it over here, you'll get this equation. But what is dv? dv is equal to dA into h. Why? See, since this is a very short glance of derivation, I don't want to go much in detail of this. So basically what we have here is, we have a disk here. well, we have a small cylinder here, okay, and the radius of the cylinder is r of z. The height of the cylinder is dz, okay. In which case, what would be the volume? The volume will be area into height. What is height? dz. What is area? Being circular, it is dA, which is pi r square. R is r of z. So the r square becomes r of z the whole square. And we have found out that r of z the whole square is r into z by h the whole square. See, now I do understand that some of us here might be okay with this derivation. Yes, some of us may want to have a detailed derivation, and that's why I said I have explained this derivation, explained the selection of disk, the stacking of disk, the cylinders in much detail. Please watch the next solution. Things will become very clear to you if you spend more time on the derivations. Okay, so coming back to this. Now r of z can be plugged in with r into z by h. So it becomes pi r square z square by h square into dz. What is this? Equal to dv. So we have this dv now, and therefore z bar can be calculated. Now it's just simple integration. So what is z bar? Integral z dv by dv. dv is integral, dv is pi r square z square by h square into dz. dv is pi r square z square by h square into dz. Now, in the next step, what we've done is, since the variable is dz, pi is a constant, r is a constant, z is a constant, and so is h. So we can take pi r square, z square, h square outside the integral in both numerator and denominator. So the only difference that comes up in the denominator is z square, whereas in the numerator is z cube. Now, what is integral z cube? Is z to the power 4 by 4, varying from 0 to h. Z square is z cube by 3, limit varying from 0 to h. So this gives us h raised to 4 by 4 minus 0 by 4, h cube by 3 minus 0 by 3, which is h raised to 4 by 4 by h raised to 3 by 3, which gives us h raised to 4 by 4 into 3 by h cube. H raised to 4 by h cube is h. So what we get is 3h by 4. Right? Okay, so the correct option here is option C, option D, 3h by 4. Right. Now let's try to visualize and understand the cone in inverted and in upright position. Well, now you might also be wondering, why can't it be, if we discuss upright and inverted, why can't it be like this? So we have the x-axis, y-axis, the z-axis. Why can't the cone say lie like this? Well, of course, yes, that is a good possibility. For that matter, the cone can even be placed symmetric to y-axis like this. It can be kept like this. There can be there can be many possibilities for the cone, and no matter which orientation you keep, the answer should definitely be 3h by 4 from the vertex and h by 4 from the base. Now, explaining every derivation becomes really complex. So what we do is we just stick to these two cases, case 1 and case 2, upright and inverted cone. All right. Okay. Moving on to the detailed explanation for upright cone.